There guys, so today we're going to talk about confidence intervals, and often you'll hear that word confidence intervals because you can calculate confidence intervals on different parameters. Usually what we're going to be interested in doing is calculating confidence intervals about the mean. And that's largely because we want to be able to know how sure we are that the true parametric mean actually falls within a range of our estimate of that mean. So once again, it's important to kind of think about a sample as being drawn from a continuously distributed normal variable with a mean of mu and a standard deviation of sigma. Okay, and these Greek letters are indicating that these are the parametric values. And so when we draw a sample, what we're doing is we're getting a particular value of y sub I, and we're going to get some mean for that sample. So for example, we might estimate it here, and we're going to get a mean of y bar. And y bar estimates the true parametric mean mu, which we really is what we care about. For any kind of test, we want to actually know about this parametric true population mean. And remember that our sample is an estimate of it down here. Our sample mean, given by y bar, is an estimate of this true population mean mu. Okay, so confidence intervals are nothing more than a way of giving a range around plus or minus some quantity around our estimate of the mean, and what we're saying is then that mu falls within that range. And it expresses also how sure we are of that, so we can actually change the outer limits of this to increase our surety that mu falls within that, or to be less sure about it. And typically we want to express the confidence interval in terms of 95% of the time we are correct in saying it's in that. That's just typical. So I need to explain to you how we go about setting those confidence intervals. Now, most of you have probably heard something like this in a past course, that the mean y bar, let me get rid of that for a sec there. All right, the mean y bar, oops, let me get my pen back there. The mean y bar is between, or the confidence interval is given by y bar plus 2 times the standard error, or y bar minus 2 times the standard error. And those are the upper and lower confidence limits. So this is the upper confidence limit, and this is the lower confidence limit. And this whole thing describes the confidence interval. So if I ask for a confidence interval, I'm asking for that entire range, okay? And then the upper and lower confidence limits are given by specific values. Okay, so what is SE? Remember, SE is the standard error, which is the standard deviation of the mean. Not the standard deviation of the distribution, but the standard deviation of the mean. And that's given by S over the square root of n, okay, where this is the standard deviation of the distribution. Okay, so the standard error, which you should have learned in a previous course somewhere, but if you haven't, go back and review that concept, is the standard deviation of the mean, and so that's what we're putting in here. And notice I've prefaced the standard deviation by a value of 2, okay? And I'm going to tell you now that that way you learned it is approximately correct. In fact, it's exactly correct, about for an n of 60. So look over in the lower left here. You're going to see me like Kilroy here, but over here in the lower left, I'm pointing out that we have an n of 60, degrees of freedom of 60, which would be an n of 61, of course. That's where we have a t value of 2, exactly. And so really we ought to be writing this confidence interval differently, because strictly speaking it's true only when n equals 61. And then we have t equals 2, and that confidence interval is correct. If we want to generalize about it, we should say the confidence interval, actually a better way to write it would be mu is between y bar and plus t times the standard error. And let me go back over here and stop looking like Kilroy. And over here at the lower end we have y bar, y bar minus t times the standard error. Okay, so mu is going to be somewhere between this lower limit and this upper limit. And we tell what t value to put in based upon the sample size. So notice how the t values get larger. So if we're going to have a 95% confidence limit, we want a two-tailed test with a 0.05 being in the tails of the distribution. Okay, and so we would choose this column here. Notice that with an n of 1, or n of 2 degrees of freedom of 1, we have a t of 12. So we have a very poor estimate of mu, because we're going to be multiplying the standard error by a very large number, right? And then notice how it gets smaller and smaller until finally with an n of infinity it's 1.96. So really for a huge population, our t value is closer to 1.96. But we just round that off to a t of 2 to get an idea. But really when you are precisely giving a confidence interval, you should use t and multiply t times the standard error and subtract t times the standard error from the mean to find out where mu is. So what is the proper way to interpret this confidence interval? It means that really kind of strictly speaking 95% of the time when we draw samples with n equals whatever the population size is, okay, 95% of the time when we draw samples of that n, mu, the true population mean, is within this interval. So, in other words, we are fairly confident, willing to make errors 5% of the time when we say mu is within that range. Now, what that means is that on the average 1 out of 20 times we're going to be wrong in saying it's within that range. And so, why is that okay? Well, because there's no reason really to, there's no rationale for doing anything different. Now, we could increase our confidence by looking over here, and we could choose, say, a two-tailed test with 0.01. That means that 99% of the time we would fall within that range. Notice that t gets larger, and therefore our interval is wider. So that makes sense, right? If we are needing to be confident 99% of the time, we really ought to have wider confidence intervals. On the other hand, if we're willing to take a bigger chance, we could go over here to two-tailed test with 0.1, we would see we have a smaller t. That will give us a narrower confidence limit, and we could have a narrower confidence limit, but we're going to be wrong more of the time in saying mu is within that range. So classically, we typically present data with confidence limits that define an interval that includes 95% of the time we would be correct in saying mu is within that range. Okay, so the confidence interval is in fact giving us a degree of confidence in our estimate of y bar. And the bigger this number is, the less confident we are about that particular estimate of y bar as an estimate of the true population mean. Okay, so that's the idea of confidence intervals, and I wanted you to have a slightly more sophisticated understanding than y bar plus or minus 2 times the standard error. That's just an approximation. It really should be t times the standard error, and it's used in order to depict means. So for example, if we have two groups and we are going to show confidence means, so y bar, and we're going to have some kind of a histogram like this. Typically, well, quite often, if we put confidence intervals, we will do something like this. And we will say that the mean and the confidence intervals are shown. Now, I will say more typically, we show plus or minus 1 standard error here, not t standard errors. But if we were showing confidence intervals, this is what we would do. Often confidence intervals are shown in tables. And so, for example, you might have a group, have a table where you have group A and group B, and you're showing the means for some experiment, and you might have 4.186 and 6.232, and you want to give an idea of, are these means different? And so you would give confidence intervals. And one way that's done is to simply put the low value down here. So for example, 3.886, and then a comma, and 4.486 if our t times SE was 0.3, just for example. And you would do the same thing over here. You would give the lower confidence limit and the upper confidence limit for 6.232, and then you could see whether they overlapped the other mean that you're comparing it with. So, so this is the lower confidence limit, this is the upper confidence limit. Okay, so that's how often these values are presented. This is the mean, and then this is the lower confidence limit and the upper confidence limit. And you can present a table of means that way, showing that that you have, it kind of illustrates the level of confidence you have in this particular value. And you're saying the mean is, the true population mean is found between these two values 95% of the time, typically, what is used. If you want to be more confident than that, you can produce a larger t, choose from over here in the table a different value. You can be as confident as you want. 0.001, for example, would mean that 99.9% of the time mu falls within that range, and you can go to your sample size, subtract 1, and look over and find, for example, a t value that's bigger, and that will produce a wider confidence limit. Okay, I will show you in class how confidence limits are shown on jump output. They're shown visually in a way that's helpful for you to inspect means and compare them. All right, that's it for confidence intervals.